Hello everyone, my name is Viraj and today we'll be looking at the 15th problem from the CP-31 sheet by TLE Eliminators under the 800 rated questions. Let's go. So I'll be moving on to my CP-31 sheet over here. I have ticked off my 800 rated parameter and we'll move on to our 15th problem, array coloring. So let's click on this. Alright, so we'll read the problem. You are given an array consisting of n integers. Your task is to determine whether it is possible to color all its elements in two colors in such a way that the sum of the elements of both colors have the same parity and each color has at least one element colored. Alright, for example, they have said if the array looks like 1, 2, 4, 3, 2, 3, 5, 4, then we can color it like this, and the sum of the blue elements, so one color is blue basically, you can see some of the blue elements would be 6, and some of the red elements they have taken would be 18. Alright, so we'll actually discuss what is the meaning of each and every statement that they have said over here. Alright, so let us quickly discuss some of the few words they have mentioned first of all, so that we have a better idea. We of course have an array with us where we start, so I'll call this array A, and we have some random numbers in this, so let's say A1, A2, A0, A1, A2, so on till A of n minus 1. So I've done a zero based indexing simple, and I'm saying this is an n sized total array. Alright, now in this array what they have said is you want to color these numbers in exactly two colors. So let's say they have picked up the colors also by choice. So I will take the color red that is given by them, and the other color I'll take would be blue. Alright, now what are they saying is they're saying simple thing. They're saying, okay, you have these elements, just pick every element and allot it some color. Condition you need to follow is that for every color there should be at least one element colored. As in, let's say that you pick up the color red. Now you cannot color every element with red color. You want to color blue also, so that would mean at least one element should be there which has blue color, and same goes vice versa. So I'll jot this point down. At least one element should be there for each color. Okay, so this is a very important point. Alright, now adding to this part, what are they saying? The second thing they are talking about parity. Now the question mark is, what is parity? So this might be confusing or a new term for the beginner. Parity simply means what is the nature of the even and odd type of the number. That is what defines the phenomena to be parity. That is what defines the phenomena to be parity. Alright, so if let's say the number is odd or let's say the number is even, that nature of being odd and even would be parity. So when I say that I want the parity should be same, as in the same parity they have written over here, that means if let's say something is odd, then the other thing is also odd, and if something is even, then the other thing is also even. So it's basically simply saying I want the same odd nature or the same even nature. Now what do I want that on? I want that on sums. And where is the sums coming from? This coloring that they have done. Alright, so we'll imagine this better now. Let's say that you start coloring the elements. Let's say you just allot, I'll randomly allot these colors. So let's say I allot this color red, I'll allot this color blue, I allot this color also blue, and then let's say I allot this, for this I allot the color red, and so on and so on. So I've just allotted the elements random colors, and when I do this, I have of course followed the first condition, that is I have always allotted for every color at least one element. Now once that is done, I can just of course collect all the elements that are kept in red, and I can collect all the elements that are kept in blue. So after I do that, I can call this as like sum r, SR, that's the sum of all the red elements. This is some value, and then I can call this as sum blue, that is sum of all the elements colored with the blue color. So this is like SB, and the parity is actually on these two numbers, that is sum of the red elements or red colored elements should have the same parity as the sum of the blue colored elements. So if let's say this particular number is odd in nature, then this should also be odd in nature, and if this is even in nature, then this should also be even in nature. This is what they are trying to ask you, and what they are saying is if you can do such a coloring system for all the elements following these two conditions, that their net sum turn out to be have a same parity, and at least one element is definitely colored for every possible color. That is in this case only two colors we're talking about. If both conditions are fulfilled, then print a yes. And if you think you can never fulfill such a condition, then print a no. So they are asking for a yes no case basically. This is like a yes no question. If yes, for such a possible reordering, such a possible coloring, that would be a better term, such a possible coloring, and no if no such possible coloring is possible. Alright, so I think the question has been generalized, it is clear now. Let us look at one of the test case and try to understand this. So very quick, we can actually look at the case they have given over here only. You have, let's say, the element 1, 2, 4, 3, 2, 3, 5, 4. Okay, I think for this is already given, so it should be very visible that we are having 6 for the blue colored elements and 18 for the red colored. Let's take up some other test case. How about I take up a very simple, let's say I'll take up this test case over here. That's 4, 3, 4, 5. 4, 5. Okay, so I'll take this over here. Let's say this is 4, 3, 4, 5. So very simple, what I can do is I can just take red and red for these two 4s, and I can take blue and blue for these two numbers, that is 3 and 5. Now if I add everything up, of course I get the blue sum as basically 8, and the red sum that I get over here would also be 8, and of course 8 and 8 both are having the same parity, which is actually even. So you blindly print yes, that I was able to color them in such a way that I can see I have allotted at least one element to every color, and I have created the parity to be even, or as in same parity. Both are having even. This is also even number, and that is also an even number. This is also an even number. Alright, so I think the test cases are pretty clear. If you pick up your pen and paper, you will be able to see all the other cases and figure out why their answer is coming no and yes, just by quickly referencing from the output. And what we can do now is actually discuss what should be my expected time complexity for this piece of question, so that again I can start formulating any idea, and on that I can build my code later on. Alright, so we'll quickly have a discussion on that part. Of course, I can see that I have some of my standard observations. I know for 1 second I am allowed 10 power 8 operations. This is something I know by fact, and I have been written over here that time limit per test is 1 second. So if I write this like this, that for one test basically I have 1 second time limit, that means basically 10 power 8 operations again. Now in every test I have some test cases that's given by the factor t. So one test basically has, in this question, approximately on a very upper bound, you can say 1000 test cases. That's pretty clear written over there. So if I simply ask you how many operations can you run for each test case, then what will you report? You will say, okay, I can run 10 power 8 upon 10 power 3. This gives me 10 power 5 elementary operations for each test case. Now, how does this help me? Of course, this helps me to create an idea that, okay, if I have n value with me in this case, how long can I jump towards a time complexity in terms of n that will later help me formulate my idea. All right. So n is given pretty small in this case. N is given only 50 over here. So if let's say I calculate n cube, that basically means this is 50 cube, which is basically like 1 to 5, and then I have 0, 0, 0. So this is kind of saying this is like, you can say 1.25 into 10 power 5 order. So this is arguably a little higher than the number of operations we discussed. Approximately you can say 25,000 elementary operations higher. But then this still works. Like if you even go in a n cube solution, this will not be a problem otherwise. So because this is in the order of 10 power 5 operations, so this would be fine to write. But that means if let's say I calculate n power 4, then that would be a problem. I don't want to run a solution that goes in n power 4 order. So keeping this acute mathematics in our picture, we know that O of n cube will work, and O of n power 4 is where we'll start having a problem. And since O of n cube works, of course, anything below this works, n square will work, O of n will work, and so on, so on, so on, even to go to a constant time complexity. If you are able to do that part, it of course works. So I have an upper bound in my picture that, okay, if I run my solution even in n cube, it will work. Now that doesn't mean I of course want to run my solution in n cube. Maybe I want to go even lower than this. Maybe I can create a very well structured solution. But then again, we have something in our mind that even if I go in n power cube order, I would not be harming my solution. I will still get an accepted, considering that my logic is correct. Okay, so this gives us an expected time complexity parameter, and this is very, very important to note every time before we actually form any solution in our mind, because this helps us reduce all the possible futile cases of coding and logics we could have formulated without even considering the time complexity they could have achieved. Now that I know I cannot go above n cube, this works. This helps me reduce a lot of my work. Alright, so now how do we proceed? I have an expected time complexity in my head. We can now move on to our actual observation, or our actual argument rather, which I can state first and we'll try to prove later. So by just reading this question and figuring out some cases of my own, I have a very strong argument I'll try to present to you. And then we'll, of course, go again with proving this part, and we'll see how does that work out. So the argument according to me is that if the count of odd numbers is odd, then answer is no, else always yes. Okay, so this is my argument that I've written over here. Now let's try to think how can we prove this. I'll try to counteract this part, and we'll see if we can actually come up with a neat observation which actually helps our argument. Okay, so we'll start off with very simple cases first. First of all, I know that an odd number, let's say if I want to represent an odd number, how can I do that? An odd number can simply be represented by something of this form, 2k plus 1, right? Where k is simply a natural number, you can say. I've taken, or rather you can say a whole number rather, where k belongs in 0 to, or even you can say k belongs in a negative range also, that doesn't matter. Just that k is a simple number I've taken on an integer line. So you can say 2k plus 1 is like a standard sort of a, you can say notation we do for an odd number. So this is an odd number over here. And how can I represent an even number? Simply, I can say this is 2k. This is how we represent normally an even number. So considering this fact, I can come up with very simple conclusion. First of all, if let's say you add up two odd numbers, that is 2k plus 1 plus 2k plus 1, what do you get? You basically get 4k plus 2. Now this number, if you take 2 common, you will get 2 into 2k plus 1, and this number is actually divisible by 2, which means that if you basically add two odd numbers, you will get an even number. And similarly, if you simply add 2k plus 2k, this gives you 4k, which means that since this is also divisible by 2, I can simply say that if I have two even numbers, they also add up to give an even number. Okay, so these are very two crucial observations that we have observed. These are like simple mathematical statements that we all know. So I'll just write them down at the top over here so that we know in our picture. All right. Okay. Now we'll discuss the next case. That is, we want to have two cases. One is we are talking about the parity since. So I'll make those two cases in that part only. When the parity of the sum is odd and when the parity of the sum is even. So let's just take case number 1. I have case number 1 with me when I say that I have created sums to have a parity of odd nature. Alright, so I think I can write this with a different color, white only, or maybe yellow. Okay, so this is case 1 where I'll say that the sum that I have created is having a parity of odd. Okay, so let's just imagine our buckets. This is my red bucket over here and this is my blue bucket. So what does I mean by bucket is simply which element I'm coloring. I'm just keeping that in a bucket. You can just imagine that as a set or anything. Simple observation, simple notation format. Alright. Now, of course, in the very starting of the question, I can observe in my array that there would be some even number of elements. I'll just call them even elements. And there would be some odd number of elements. Okay. Now, since we have already checked that currently our sum of the red bucket is 0 and the sum of the blue bucket is 0. Now 0 in its own sense is an even number, right? We start off by saying that, okay, 0 is an even number. So if let's say I have my even elements bifurcated over here from the array, and if let's say I just start placing them in these red and blue buckets one by one in a random order, do you think the parity of these red and blue buckets change? No, because initially you can see that the sum is 0. Now if let's say you add an even element to this, can you see that over here? Very important observation. If you have even sum initially and you add an even element to it, you still get an even number. So can you say that the parity of this red bucket changes? No, it does not change. And same goes for the blue bucket. So this is very important. If I add an even element, or you can say simply even element does not change parity of sum. Change parity of sum. This is a very, very important point. Now, if I have observed this part, let's move on. So I can say that if the even elements are not changing my parity, then maybe I'm not bothered with them because they're not helping me create the odd parity, right? You know that if you are adding even number to the bucket, you are not changing the parity. If they started with even, they are still remaining even, but the case we're talking about is odd parity sum. So if I'm not creating odd parity sum up till now, that means after I've exhausted these even elements, I'll be left with the odd elements only. So these are not of my concern anymore. I will just bifurcate them in a random order to each bucket. If let's say I have some even elements and my energy would only go to the odd elements. Now let's argue. If let's say you have the odd elements, let's say 4 in number. So what you can do simply is, you can just keep, alright, I will have let's say 3 elements of odd nature in the red bucket and one element of odd nature in the blue bucket. Now what does that help me do? Of course the blue bucket will have a parity of even up till now. Now if you add one odd element to it, what happens? Clearly observe over here. If let's say you have an even element and let's say you add an odd element to it, what happens? So I think I just missed this point over here. Let's just write one more point over here. We observe that an odd plus odd gives you even, but one thing more. How about an odd plus even? What does this give you? This gives you an odd number? Yes. So can that mean that if let's say up till here, the parity was totally even, then if I add an odd number to it, can I say that now the parity of this whole bucket becomes odd? Yes, it does, because now you have added one odd element in it. Now what about these 3 odd elements? Why did I keep it over here? How is it helping me make the red bucket's parity odd? It's helping me because I have kept 3 odd elements. Now in these 3 odd elements, of course, 2 pair of odd elements can just club together and make an even. So odd plus odd gives me even, I know this. So eventually out of these 3 elements, 2 elements will go off and just capture one even element position, net even element, and that is not going to affect the parity. But that one extra last element is going to help me again create an odd parity even for the red bucket's sum. So this eventually creates an odd parity at this bucket also, an odd parity at this bucket also, which means I have created an odd sum. Alright, now let's counter at our argument in this case itself. Let's say that you can very clearly see that I have taken the odd elements count to be 4, which is actually even. My argument was that the count of odd elements, count of odd numbers, if it's odd, then the answer is no. So we just saw the answer for yes case, right? Now, if let's say this would have been 5, then what can you do? Let's see. So if I have 5 elements and I want to create an odd parity, for example, I want to create an odd parity, I cannot do any bifurcation. Imagine, how can you make sure that you receive an odd parity in both the buckets? So let's say you have these 5 odd elements, okay? So you will place one odd element over here, one element over here. Let's say you place one more element over here, one more element over here, and then the final element at this place. Can you see that basically 2 odd elements are going to pair up and their parity is going to become even? So blue bucket's parity still remains even. And what about this part? Can you see that you have 2 odd elements? They will club up to have a parity of even, so they are gone basically. And this one odd element that's there is going to make the red bucket's parity as odd, and this blue bucket's parity still remains even. So the parities don't match, and that's the case. If you have odd number of total odd numbers, then you cannot bifurcate them or place them in the red and blue colored buckets, or simply you can say red and blue coloring, so that you actually achieve same parity at the end. So this is just a counter proof I have given you for case number 1. That is the odd case. All right. Now, of course, we can extend this to our even case. All right. If let's say I want to create my even parity, this is going to be same case. All right. So this is case number 2. This is if I want to create an even sum. Same thing again. I have, of course, a red bucket. I have, of course, a blue bucket. And then initially I have some even elements, and I have some odd elements. Now, same thing. If I have some even elements, I'm hardly bothered with them because I start off with even sum over here. I just keep on adding them at random places and the parity still does not change. So I just exhaust them, it doesn't matter. But what about the odd elements? Same thing again. If let's say I have, same thing, if let's say I have 4 elements, that is even number of odd elements, I can just give 2 elements over here, 2 elements over here. Or if let's say I have 8 elements, I can just give 4 elements over here, 4 elements over here. Or basically even number of odd elements at this place, even number of odd elements at this place. I know that is going to create an even parity because we know that even 2 odd numbers are going to club together for an even, and that even number again doesn't change. The parity still remains even because you started off with 0 as a sum that was initially even. But what happens if you have your odd elements as 5? Same case again. Can you bifurcate them to create an even sum? No, we just saw you had difference in parity. One was odd, one was even. So you will be always forced with creating different parity sums if odd number of elements are odd in nature. Correct? This is again a very trivial observation. You can of course verify this more if you create some test cases. If we run this sample thing through our test cases over here, this is going to make much more sense. You will get a full load of what is we are trying to capture and what idea are we trying to picturize. Alright, so the mathematics is very, very simple to understand, and this is what clubs our whole idea. This is what the argument proves. So if the count of odd numbers with me is odd in the array, then the answer is straightforwardly no, because I know always I'll be at the very end in a haphazard problem where I'll not be able to create the same parities. Else the answer is always yes, because if I would want to create an odd parity sum, I will be able to do that. If I want to create an even parity sum, I'll still be able to do that. My whole dependency is basically on the odd numbers and how many times are they coming. Okay, so very, very good question, I should say. Requires very trivial observation. Let's just quickly look at the code part now to understand how can we implement this out. If you understand the logic, code would be very, very simple. I'll just show you the code. All right, so we'll take up the test cases. Run a loop on the test case part. I'll take up the n as the variable for the size of the array, and I'll just take the input of the array. Now I have a variable count of odd numbers. I'll just go in my array. If I think that ai modulo 2 is 1, this is basically the check for odd. If modulo 2 value gives me 1, that means this is an odd number. So I'll just increase my count of odd by 1. Else I'll simply say don't increase this. So this condition, if it's true only, then this counter increases, and when I come out of this for loop, of course this gives me all the elements, or sorry, the count of the odd elements in my current array. Now what is the check I want to do? Is this count also odd? Is this count odd? How do I check that? Count of odd, that's the element, should mod 2 give value as 1. If it does, the answer is no, because I know then I can never create same parity sums, else the answer is yes. Alright. So very, very simple code, very, very simple logic. Let's discuss the time complexity now. This runs in n order because you have taken the input of the loop. This runs in n order again. Up till here you will of course taking the inputs, and then you will have a very simple elementary check on mod 2 value and mod 2 value over here outside. So no extra time complexity. So if I discuss and write the final time complexity, I know that the superseding term is basically O of n. And now since n was in order of 50, this is a very good, I should say, time complexity we have achieved. O of 50 will run very fast, not going to get us a TLE. It will definitely get us an accepted solution. And what about a space? Space complexity, of course, is dependent on O of n again. That's the size of the array we are taking, which is again O of 50 only, because that is the maximum size we can go in terms of the array. So a very fun problem, I should say, and the idea making, the case making in odd and even parity was very, very important. If you get that part, this is a very simple question. Just requires these elementary mathematical statements that we should always remember. Odd plus odd gives even plus even gives even, odd plus even still gives you odd, and so on. So based on that case, this question was boiled down to a very simple case making. Alright, so this brings us to the end of our problem. I hope you like the video. Thank you for watching.